Okay, so I got two more here. Compared to the previous ones that we've just done, you'll notice that these are simple supported beams, not fixed ends. And also, this looks like a pretty simple structure to do. There's a lot of these in the world, kind of a simple supported beam with a point load. If I asked you to write the equations for shear force and bending moment, it would be not hard, but it would be some work because you'd have to write a set that's good over the first half of the beam and a second set that's good over the second half. So you can see that the approach of writing a function, even for something simple, can be quite challenging. And if I had multiple concentrated loads, that would just 3 sections, 4 sections, 5 sections. But actually, the graphical technique is really efficient at doing point loads, as you'll see. So again, just to get you started, I'm going to tell you that the reaction on the left side is P over 2, and the reaction on the right side is P over 2. I think you can probably see that's true. The load is right in the middle. You'd expect it to be evenly distributed. Now, when I start to draw my shear diagram, let's remind ourselves that we know that the change in shear is the area under the load curve, and that the slope of the shear diagram at every point is given by the loading. So starting on the left side, what is the shear force on the left edge? I go up and my force is up. So what kind of shear force is that, positive or negative? Yeah, it's making my beam rotate clockwise. So that's positive. So I'm going to start at a positive P over 2. What about on the far right side? What kind of shear force is that?
Negative.
Yeah, it's negative because you see it's trying to push it counterclockwise. So that's a negative shear force, and that should be negative P over 2. So if I can't connect these points with the logic, with these relationships, then something's not right. That kind of gives you a little check. So most of the time, you're kind of going to know where you're going to start, and you're going to have some idea where you're going to finish. So I can't do this change in shear under the whole curve because it's discontinuous. So I have to do it just over the first half. So I'm looking at the area under the load curve from 0 to just to the left of that P. Well, what is the loading? 0. So there is no change in shear. So my P over 2 is going to stay P over 2. And the shape of the curve that connects these 2 points? Well, it's given by this relationship. It says, it's just the value of the load. And what's the value of the load everywhere from 0 to L over 2? 0. 0 slope, horizontal line. So again, we can see that the shear is constant over the first half of the structure and is P over 2. Now, as I go from the left side to just to the right side of this force P, what happens to my shear? Yeah, remember also that the change in shear is equal to the value of the load. The value of load there is minus P. So P over 2 minus P gets me to minus P over 2. Now I can see in my graph that the change in shear better be 0, and let's see if it is. The change in shear is the area of the load curve. And what's the area of the load curve here? Well, there is no load, so it's 0, so that works. Yay! I like that. And what's the shape of the curve? What's given by the load? Again, the load is 0, so we have a curve that has a constant slope of 0. So there you go. So you have a beam that has positive shear of P over 2, then you cross under the load, and it's the same value, but opposite direction. Okay? Now what do I do about the moment? Well, let's look at our moment. Do I know the moment anywhere?
Yeah.
Yeah, what's the moment right there at A, or the first pin? 0. About the other reaction? 0. Pretty cool, huh? Now you'll notice the shear diagram is discontinuous. So when I apply my relationship between moment and shear, the fact that the change in moment is the area under the shear diagram, right? Well, I've got two different areas I have to deal with. This first area is positive. So it says the change in shear is the area of this diagram, and that's a rectangle. We know the area of a rectangle. It's base L over 2 times height P2, P over 2. So that's going to be PL over 4. And the second part, the derivative relationship, is that the slope of the moment diagram is given by the shear. And you notice the shear value everywhere in this range, 0 to L over 2, is constant and positive. So here is a curve with a constant positive slope. In fact, if I asked you what the slope of that diagram would be, you would tell me it's P over 2. Now from the middle of the beam to the right side at L, the change in shear here is given by this part of the curve, which is what? Yeah, it's a rectangle, base L over 2 times the height, which is minus P over 2. So that's minus PL over 4. So you start at PL over 4, you subtract PL over 4, you get 0. All right, we found our way home. And what's the slope of that diagram?
Negative P over 2.
Yep, it's given by the shear, and the shear is constant and negative. And there's a curve for that. And if you were to account for that slope, you would see this is minus P over 2. And there's your moment diagram. Where is the maximum moment? Where does it occur?
At the center.
At L over 2. What is the value?
PL over 4.
PL over 4. So this would be one that you'd want to do probably graphically, not write equations for. You could write equations for it. Don't get me wrong. You can. But I think the graphical method is a lot faster. All right, let's move over to this one. Or any questions about that one? You can see they're kind of going up in complexity. So what do you think the reactions for this beam are? What's the reaction here? Probably half of the total load, right? What's the total load? W naught L. So you're going to have a force here of W naught L over 2. And over here also will be up W naught L over 2. So now I'm going to start and try to draw my shear equation. We use my relationships here. So where am I going to start shear? What's the shear at the beginning point? It's the force that's acting up. Is that positive or negative shear? Positive? You don't sound very positive about that. Yeah, it's positive. Why is it positive? Yeah, because this end of the beam wants to rotate under that force pushing it up. It wants to rotate clockwise. What about the other side? What's it want to do? Rotate counterclockwise. So it's going to be negative, right?
Yeah.
So again, I know where I'm starting. I know where I want to end. Let's see if I can connect the dots. So what is the change in shear between the left edge and the right edge? What would be the total area under this load curve? And what is that area? Base times height, L times W naught, and it's positive or negative? It's negative. You got positive W naught L over 2 minus W naught L gives you negative. The shape of the curve is what? Given by the load. And the load is constant and negative. All right, let me try to draw this a little more to scale. I don't think my graph is to scale, but you'll get the idea. Now you'll notice something has happened here. We have crossed the x-axis. In fact, what I'm going to do is I'm going to not sure what that is. In fact, I'm just going to call that some distance x1. I need to find out what that value is. Why do I care about that? Well, two things there. What? The shear is 0. What do we know what happens when the shear is 0?
The moment has a slope of 0.
Yeah, so that means that the shear is 0. That means the derivative is 0. That means it's going to be a max or a min. That's an important point for us. And what else? In order to find the change in moment between 2 points, I have to get the area under the shear diagram. Well, what's the area under this part of the shear diagram? What's 1/2 base? What's the base? Don't know. So I'm going to show you a way I think is pretty nice that works in general. So what I like to do is to extend this line up and actually use the equation. I'll say the change in shear. What is the change in shear between here and here?
W naught L over 2.
But how does it change? Positive or negative? Negative. So the change in shear is minus W naught L over 2. What is the area under the load curve for the same segment? If I come up here, I'm looking for this area. We know the bottom is x1, right? I guessed what that was. What's the area of that curve? Well, it's base times height, right? X1 times W naught, and W naught is negative. These two things are equal, right? The equation says they are. So I now have an equation that says W naught L over 2 is equal to W naught x1. I just multiplied both sides by -1. Can I solve for x1? What is it? L over 2. You can apply that same strategy to just about anything. Now this one obviously is not the right word. This one makes sense that since these triangles have to be similar, and if they have the same height, they should have the same base. They have the same base and the total length is L. It makes sense that they're L over 2. They don't always work out like that. But this kind of strategy where you go back to your fundamental equation that we've used over and over again now and use it to your advantage, you can figure that out. So now I know this is L over 2, I can proceed. Because I know the change in moment between any 2 points is the area of the shear diagram. Now I can calculate this area of the shear diagram. So what's the moment at the starting point? 0. And when over here at the roller? 0. So now I'm looking at the change in moment as the area of my shear diagram, and this is the area of my shear diagram. So what is it? Well, it's L over 2 times WL over 2. That's WL squared over 4. And what's the shape of the curve in between? Well, it's given by the shear. So I start at the beginning. My shear value is W naught L over 2, and that's a positive value. There's my positive slope. And it decreases to a value of 0. So here in the middle I should have 0 slope. And you can, what was the thing you said, Mr. Van Tilburg? What am I doing? I'm sketching a burpee or something? Swagging a curve. I'm swagging a curve that looks like half a parabola. How does it behave on the second half? Well, the change in moments, the area of the shear diagram. The area of the shear diagram is 1/2 base L over 2 times height minus W naught L over 2. And that's the negative of this. That does bring us back to 0. So what's the shape? Well, we start with the values of the shear. That'll tell us the slope. So I start here. Well, it's the same value, right? 0. And now it gets progressively bigger. But it's what on the other side? Positive or negative? Negative. There's your negative slope. So let's swag a curve. Who says that? Dr. Meyer?
Yeah.
That's cool.
Thank you.
I think I'm going to start greeting him in the hallway like that. Any questions about that? Good, because let's work some more.